Greetings, chemistry students. Today we're going to pick up with the Bohr model of the hydrogen atom. We talked about that some yesterday. I just want to go over a few key points with you about all of that. So according to the Bohr model, which is on the back of your reference tables, we've been dealing with this yesterday. According to that, the electrons circle the nucleus in fixed energy levels or orbitals, and they're represented by n equals 1, 2, 3, 4, 5, and 6. N standing for energy level. And the electrons have a fixed amount of energy within each level, but they can gain or lose energy by moving to a higher or to a lower level. They gain energy when they move to a higher level. They lose energy when they move to a lower level. And so, yeah, the chart on page 8 of your reference tables is key. And orbital 1, of course, is the lowest energy. The thing about this Bohr model is it only works for hydrogen, because once you get past hydrogen, you have more than one electron, and the electron cloud becomes more complicated. So the Bohr model works great for hydrogen, doesn't really work for any of the other elements. But it was a good conceptual foundation of how electrons work, just not fully fleshed out and detailed. And that's because this model is fundamentally flawed. Electrons don't move in circles around the atom like planets around the sun. Right. So the modern model of the atom is called the electron cloud model. And it says that electrons behave as both particles and waves. So it's got wave-like properties and particle-like properties. And the electrons have these clouds or regions of probability where they're likely to be found. So essentially, what we're using is what's called a 90% confidence interval is what these clouds are. If you ever take stats, you'll learn about confidence intervals. But that's where you're likely to find the electron, but it can be anywhere in that spot. Now, the electron cloud has a lot of different divisions. Just like if you've ever been to a sporting arena, I know you can't go to those right now because of COVID, but if you go into a big arena or a large theater, you have different levels, and then you have sections, and then you have rows and seats. And so when you look at your ticket and it tells you what level and what section and what row and what seat, you have a unique ticket that gets you to a very specific seat in that arena or in that theater. The electron cloud works similarly. It's got different divisions that designate a specific region that applies to specific electrons. So the electron cloud has several different divisions. The first is energy levels. There are 7 different energy levels in the electron cloud. Also, on the periodic table, there are 1, 2, 3, 4, 5, 6, 7 different rows on the periodic table. Interesting coincidence. Then there are 4 different sublevels that are symbolized with the letters S, P, D, and F. Those used to refer to specific spectral lines that you would see through a spectroscope. S, P, D, and F ultimately stand for the terms sharp, principal, diffuse, and fine. There's 4 sublevels, and on the periodic table, there are 4 different regions of the periodic table. We've got this little region over here. We've got this section over here. We've got this lowered section in the center, and then we've got this little section down here. Is that a coincidence? We'll find out. Then, within the sublevel, there are orbitals, which are the 3-dimensional regions of space where you are likely to actually find the electron. And each orbital can hold 2 electrons. So unlike seats in a movie theater or at an arena where the seat only holds 1 person, these orbitals hold 2 electrons, kind of like seats on a school bus, I guess. So you don't need to know this next slide, but this is kind of showing you that you have the S, P, D, and F sublevels. They have different amounts of orbitals, and so since each orbital holds 2 electrons, holds twice as many electrons. Now with these 2, 6, 10, and 14, interestingly enough, this section of the periodic table is 2 elements across. This section is 6 elements across. This section is 10 elements across, and this bottom row is 14 elements wide. Interesting coincidence. Now, the first energy level has one sublevel, the second has two, an S and a P, the third has an S, a P, and a D, and the fourth, fifth, sixth, and seventh have S, P, D, and F sublevels. Now, you don't need to bother writing all that down, but if you put all this together, you get a chart that looks like this. And I'm going to upload a version of this chart that you can reference for yourself when we're going through all this. So this shows the lowest energy down here. Just kind of imagine the nucleus as being all the way down here at the bottom, and the electrons fill up as you get away from it. So the goal in all of this is essentially electrons are negatively charged. They're attracted to the positively charged nucleus. They want to get as close as possible. Just like if you're going to a concert, typically you want to be as close to the stage as possible. But electrons are not quite like people. There's very specific rules that they follow, right? So there's 3 rules that we're going to look at. You don't need to know them by name. You just need to know how to actually follow the rules. So the first rule is the Aufbau principle. Aufbau means, it comes from the German phrase meaning to build up. And all that says is that the electrons go in the lowest energy level orbitals possible. So they start at the bottom and they build their way up. Kind of like if you're building a brick wall, you start at the bottom, laying the bricks at the bottom, and you build your way up. You do the electrons into the electron cloud similar way. They start closer to the nucleus and then get further away. Second is called the Pauli exclusion principle, which says that each electron has this property called spin, which we are representing with up arrows or down arrows. And so 2 electrons can occupy an orbital, but only with opposite spin. If you want to visualize it, you can envision electrons as literally spinning, and it'd be like one spinning clockwise and one spinning counterclockwise. That's not really how this works. It has to do with their magnetic properties. It's like being a magnetic North Pole or a magnetic South Pole, since electricity and magnetism are pretty much the same thing. So these electrons generate magnetic fields. They just have to create opposite ones in order to fit together. And Hund's rule says that electrons will only pair up when all the orbitals of that sublevel are occupied. So Hund's rule is basically like when you go to get on a school bus in a non-COVID environment, you're typically going to take an empty seat unless there are no empty seats, and then you'll ask somebody if they mind scooting over and sharing the seat with you. So if we go back to this diagram, we're going to actually look at how we would draw out some of the elements. And I'll put a copy of this entire presentation in so you can manipulate it. It's just the arrows, for some reason, don't line up when I converted this PowerPoint to Google Slides. But I'll let you play around with this entire thing as much as you want to. So if we wanted to do an orbital diagram for hydrogen, it's just got one electron. It's going to go in the lowest energy sublevel right down here. It's going to go in the 1s. It's going to look just like that. If we wanted to do an orbital diagram for helium, helium has 2 electrons because it's atomic number 2, 2 protons, 2 electrons. So its first electron will go down here. And the second electron will also go here, just with an opposite spin, because the overriding rule is if there's seats down close to the nucleus, you fill those first. So let's look a few more. If we look at lithium. So lithium right here, it's got 3 protons. So you're going to put the first 2 down here, and then you put the third one in the 2s. Let's take a look at, let's go with carbon, which has 6 electrons. So we go 1, 2, 3, 4. And then in the 2p, we've got 3 different orbitals here, 5 and 6. So that would be the orbital diagram for carbon. If we did something like fluorine, which has 9, you go 1, 2, 3, 4, 5, 6, 7, and then we start pairing up again, 8, 9. So that's an orbital diagram for fluorine. Let's make things a little more interesting. Let's say we wanted to do an orbital diagram for cobalt, which is element number 27. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And here, if you look closely, 3D is closer to the nucleus than 4P. So we're going to move into the 3D sublevel. So it goes 1s, 2s, 2p, 3s, 3p, 4s, then 3D. So we're going to go 21, 22, 23, 24, 25, 26, 27. So that would be an orbital diagram for cobalt. You can see that these could get rather time consuming if we're drawing them for elements. Like if we were drawing one for, I don't know, Neptunium down here with 93 electrons, it could get really complicated. I mean, it would, let's see, you'd be looking at something, I didn't even put enough arrows in there to make that one. So you can get really complicated with the D's and the F's and all that good stuff. But that's how you do an orbital diagram. Right? Now, what we will talk about tomorrow is that there are some shortcuts that we can use called electron configuration notation.